What is nuclear transformation?
Nuclear transformation is a change of one element to one another. It is performed by either fusion, joining two light protons to create a helium atom, and fission, splitting a larger nucleus to smaller nucleus. In this video, you are expected to first, distinguish among alpha, beta, and gamma decay. Second, written nuclear reaction and nuclear decay equations. Third, explain the concepts of activity, decay constant, and half-life of a radioactive sample. Fourth, differentiated nuclear fusion and fission. Fifth, cited the examples of medical and biological effects of radiation exposure as well as the practical uses and application of radiation.
Alpha, beta, and gamma decay. Types of radioactive decay. Alpha decay. When a radioactive particle disintegrates by emitting an alpha particle, the atomic number decreases by 2 and the mass number decreases by 4. The alpha decay can be expressed as follows. Example: beta decay. When a radioactive particle disintegrates by emitting beta particles, the atomic number increases by 1 and the mass number remains the same. Beta decay can be expressed as follows. Example of beta decay. Thorium is converted to protactinium due to beta decay. At a time, both alpha or beta decay are emitted. Both alpha or beta decay are not emitted during a single decay. Gamma decay. When a radioactive nucleus emits gamma rays, only the energy level of the nucleus changes, and the atomic number and mass number remains the same. During the radioactive disintegration of radium into radon, gamma ray of energy level 0.187 million electron volt is emitted when radon returns from the excited state to the ground state.
Written nuclear decay and nuclear reaction equation. First, when we say written nuclear decay, it is the process by which an unstable atomic nucleus loses energy by radiation. Next, let's proceed to nuclear reaction equation. When we say nuclear reaction equation, these are the process in which one or more nuclides are produced from the collision between two atomic nucleus and a subatomic particles. An example of alpha decay is the uranium. This is the equation. An example of nucleus that undergoes alpha decay is uranium-238. In this nuclear change, the uranium atom is transmuted into an atom of thorium and in the process gave off an alpha particle. Look at the symbol of alpha particle. The bottom number in a nuclear symbol is the number of protons. That means the alpha particle has 2 protons in it that were lost by the uranium atom. The 2 protons also have the charge of positive 2. The top number, 4, is the mass number of protons and neutrons in the particle. The next that we will discuss is the beta decay. This is the example of beta decay. The example is thorium. The example is thorium-234 is a nucleus that undergoes beta decay. Here is the nuclear equation for the beta decay rather. The mass number assigned to an electron is 0, which is reasonable since the mass number is the number of protons plus neutrons. and an electron contains no protons and no neutrons. The atomic number assigned to an electron is -1 because that allows a nuclear equation containing an electron to balance atomic numbers. Last to be discussed is the gamma radiation. Gamma radiation accompanies nuclear reaction of all types. In alpha decay of uranium-238, two gamma rays of different energies are emitted in addition to alpha particle. Here is the example of gamma radiation.
Good day everyone, so at this point we're going to discuss the half-life and the nuclear decays of a radioactive sample. So all elements have unstable isotopes, which are more susceptible to breaking down or decaying than that of the other isotopes of an element. So when atoms decay, the number of protons in their nucleus changes. Since the number of protons in the nucleus of an atom determines what element that atom belongs to, this decay changes one element into another. So different isotopes decay at different rate. And one way to measure the decay rate of an isotope is to find its half-life. So what is half-life? Half-life is the time that passes until half of the sample has decayed. So when we look at the radioactive nuclei, it is impossible for us to know when one atom will decay because it happens spontaneously and at random. A great example of this is when we have a bag of coins. So if we look at one coin, there's no way of knowing whether it would fall into tails or heads when we shake the bag. But if we look at all the coins in the bag, we'd roughly know that half of the coins will turn into heads and half will turn into tails. So if we have 100 coins and they all start as heads or unstable nuclei, after one half-life or one shake of the bag, roughly half or 50 of the coins will turn into tails. Notice we still have 100 coins, but 50 already decayed or turned into tails, and 50 are unstable and are capable of decaying. Half of the remaining unstable nuclei will decay in the next half-life, or one shake of the bag. For the remaining amount will decay in the following half-lives. And this is exactly how it works with radioactive nuclei. And again, we define half-life as a time that passes until half of the sample has decayed. So next is the nuclear decays. Unstable nuclei, whether naturally occurring or created in the lab, break apart or change into stable nuclei through a variety of processes known as radioactive decays. So what is radioactive decays? So it is the emission of energy in the form of ionizing radiation. So unstable nuclei have too many protons or neutrons upsetting the strong forces or nuclear forces. So simply, radioactive decay happens when unstable nuclei balance themselves by giving up their excess protons or neutrons to become stable.
Nuclear reactions are processes by which one or more nuclides produced from the collision between two atomic nuclei or nuclei, or one atomic nucleus and subatomic particle. The nuclides from the nuclear reactions are different from the reacting nuclei, which commonly referred to as the parent nuclei. There are two notable types of nuclear reaction, which nuclear fusion reaction and nuclear fission reaction. The former involves the absorption of neutrons or any relatively light particle by a heavy nucleus, which causes it to split into two or more lighter nuclei. The term nuclear reactions are generally used to refer to the externally. Therefore, the following processes cannot be classified as reaction. Nuclear scattering processes are processes subsequent separations of atomic nuclei without any notable changes in the nuclear composition. Nuclear decay, a process through which an unstable nucleus emits radiation in order to lose energy. Spontaneous fission reactions. Nuclear fission reactions do not require neutrons to proceed and are therefore not induced. And now, let's tackle the two notable types of nuclear reaction, the fusion reactions and the fission reaction.
Nuclear fission and nuclear fusion. First, we are going to tackle the nuclear fission. Nuclear fission is a reaction in which the nucleus of an atom split into two or more smaller nuclei. The fission process often produces gamma photons and release a very large amount of energy, even by energetic standards of radioactive decay. So we will give you an example of nuclear fission. An important example of nuclear fission is the splitting of the uranium-235 nucleus when it is bombarded with neutrons. Another example of nuclear fission is the splitting of the plutonium-239 nucleus. So that is nuclear fission. Next, we're going to tackle the nuclear fusion. Nuclear fusion is a reaction in which two or more atomic nuclei are combined to form one or more different atomic nucleus and subatomic particles. The difference and products is manifested in mass between the reactants and products is either the absorption of energy. So I will going to give you the example of nuclear fusion. The temperature at the sun's core is around 15 million degrees Celsius. At this temperature, coupled with very high pressure, two isotopes of hydrogen, deuterium and tritium, fuse to form helium and release a massive amount of energy in the form of heat.
The use of radiation in medicine is now pervasive and routine. From their crude beginning 100 years ago, diagnostic radiology, nuclear medicine, and radiation therapy have all evolved into advanced techniques and are regarded as essential tools across all branches and specialties of medicine. This video will present to you the nuclear transformations. So, at the end of this video, I am expected that you have cited the medical and biological effects of radiation exposure as well as the practical uses and application of radiation. This is a radiation exposure. Radioactive materials give off a form of energy that travels in waves or particles. This energy is called radiation. When a person is exposed to a radiation, the energy penetrates the body. For example, when a person has an X-ray, he or she is exposed to radiation. What is an example of useful radiation? In medicine, hospitals uses radiation in a wide range of ways. X-rays, CT, and PET machines uses X-ray and gamma radiation to produce detailed images of the human body, which provide valuable diagnostic information for doctors and their patients. What is a biological effect? A biological effect is generally defined as the response of an organism, a population, or a community to changes in its environment. What are the biological effects of radiation exposure? Exposure to a very high level of radiation, such as being close to an atomic blast, can cause acute health effects such as skin burns and acute radiation syndrome or the radiation sickness. It can also result in long-term health effects such as cancer and cardiovascular disease. The discovery of X-rays at the end of the 19th century was undoubtedly a significant milestone in the development of clinical practice. Advances in radiation based on diagnostic and interventional procedures since then have brought about huge benefits for patients. However, exposure to increased levels of radiation does carry some significant risks.